post-trade settlement optimization algorithm by Group 30. Let's see what is a trade settlement. It is the act of exchanging securities and cash between buyers and sellers. But there can be failures sometimes. Let's look at how it happens.
Bob promised to sell 100 securities to Alice. But Bob now has only 80 in his hand. So, there is no enough securities to sell.
Alice promised to buy securities for $100. But Alice now has only $80 in her hand. So, there is no enough money to buy. So, the objective of the project is to optimize the transaction settlement process by achieving a lower transaction failure rate within a minimum time period. When settling, the priorities and linkage dependencies in and between the transactions should also be handled.
For achieving the objectives you heard, we have used a combination of graph theory and bulk synchronous message passing. Let's see the process step by step.
The first step is to convert the transaction data set into a graph. If we use a graph, it will give us the benefit of identifying the hidden patterns between the transactions. For this graph generation and visualization, the Python Deep Graph library was used.
Cycle detection in the graph is the next step of the process. The cyclic set is used for two main reasons. The first reason is to avoid the repetitive message passing within a cycle. If not, the return matrix obtained after message passing will have many entries from the same edge value. To settle possible virtual securities, a bottleneck value is needed. It is also obtained from the cycle detection process. For cycle detection, a node-centered algorithm based on a previous research was created. Since time reduction is a main objective of the project, a parallel synchronous message passing technique was used. Message passing is the most crucial part of the algorithm. The basic principle of this is to distribute transaction details and security account details within the network at node level. A problem-specific message passing algorithm was implemented underlining this fundamental principle. The main outcome of this process is the return matrix, which presents the main reference for the settlement model. The matrix consists of a return value for each security account based on the possible future rewards, which can be accessed from that account. This is implemented based on Q-learning's Q-value table, message passing and greedy method. The main objective is to guide the trade settlement model to traverse through the optimal path. Our problem deviates from other existing problems and solutions from this dependency handling feature. There are dependencies between transaction accounts. Those dependencies are categorized into two as priorities and linkages. Priorities are pre-assigned values that are defined via the settlement agreement. Linkages are of three types. Those are with, before, and after. With linkages say that two transactions should be settled parallelly. Before and after linkages say that two transactions depend on each other. One should settle before the other. The last step of the process is the settlement. Transaction settlement is carried out using the same message passing technique. This process is performed concurrently. For a single iteration, each node settles one particular transaction, partially or fully, based on the share balance, and the optimization model's suggestion. This selection is done based on multiple dependencies, which are considered in Lexisort order. Open to settle dependency, priority values, the return matrix values, linkages, and the remaining balances of the accounts are those dependencies. This settlement can be divided into several iterations. First, the linkage dependency transactions are settled. Then settle all the non-cyclic paths using the suggested optimal value. After that, all the remaining balances are settled. Finally, the cyclic paths are virtually settled using the bottleneck values obtained when detecting cycles. Before moving into results, I'll explain the datasets we used. For transactions without linkages, we generated a synthetic dataset consists of 1 million security transaction data within 200,000 customers. For transactions with linkages, we created a custom dataset consist of small sub-datasets. Each dataset represents the possible edge cases. In the evaluation, the results of all the datasets are accumulated to a single results table. Results for with and without linkages transactions. First, the without linkages transactions. Results were compared with Gurobi linear solver. According to the results, the performance of the model does not degrade with the input size. The existing settlement models in the industry achieve a settlement ratio of around 80 to 85%, while our approach achieves a settlement ratio of 85 to 87%. Let's move into results for with linkages and dependencies transactions. These results cannot be compared with any existing solutions because it is a problem-specific scenario. Our implemented model is capable of achieving a 100% settlement rate for the tested datasets. However, in the real world, the scale of the input will be larger. So the settlement ratio can degrade eventually.
Existing solution takes 180 seconds with a settlement ratio of 80% to 85%. Our solution takes 90 seconds with a settlement ratio of 85% to 87%. So, the main objectives of the project are achieved.
It's all about the final year project of our group. Thank you for watching.